Okay, here we are starting out. Going to take a look at the review of basic physics problems. And what we're going to do is we're going to walk through and just kind of see how these problems actually work out. Now, I'm going to change things up so they aren't exactly the same as what you see in the problems, but they're going to be very similar. And I just kind of want you to get a flavor, a feel for, the types of things that we're going to be asking here. Control Z is a wonderful thing. Let's see. So let's change this. All right, so let's kind of go through these 13 problems and let's see what we have for us here and how we might be able to go through and work through these. So let's use the standard SI prefixes to express this. So rather than 10 to the 6 phones, how many phones might we have? Well, if you do a search, you can find something like SI prefixes and symbols used to denote powers of 10. We can find something here to match up with that. So if we have 10 to the 6 phones, and we notice here that we have 10 to the 6th, that's the same as mega. So we could go here and we could say we have 1 megaphone. Not like, something that makes it louder, but if you just focus in on the fact that we're trying to get the powers of 10 to be the same, then this is going to be 1 mega, 10 to the 6th. How about this one? If we go through and let's change that to, say, 2. We have, and phones, lumps, peds, what have you. I mean, the unit is just, or whatever it is we're measuring, it could be anything. So we're just putting it at that as just objects so that, we have something, some fraction or some multiple of something. That's what it's there for. So 10 to the minus 2 phones, what could that match up to? Well, looky here. That matches up to the prefix centi. So if we go back here, we could have 1 centiphone. Okay. Let's not use 10 to the 12th. Let's say we've got a real rash breaking out here. So let's 10 to the 15th lumps. What might that end up being? Well, if we go here, 10 to the 15th is peta. So we have 1 peta lump, or lumps, plural. Let's not do 10 to the minus 1. Let's do 10 to the minus, I don't know. We've got, let's say 3 down there, but we've already tried that. 10 to the minus 1, peds. What might that match up to be? Let's go here. 10 to the minus 1 and deci. So we've got 1 decipede. Ten to the minus 3 boos. We could change that to say 10 to the minus 6. So if we have 10 to the minus 6, that's micro. So here we have 1 micro boo. Let's say here we have 3 times 10 to the 6 mockingbirds, where we already looked up here. And 10 to the 6th is 10 to the 6 phones is 1 megaphone. So 3 times 10 to the 6th, this will be 3 mega mockingbirds. All right. So you get the general idea there. And that's what I'm looking for there in problem 1. So if we go down to, say, problem 2, we've got to how many milliseconds is a 3/10 of a second radiographic exposure equivalent? Okay, well, the answer, and again, that's not the same problem as what I'm having you work on, but here we've got the answer is going to be 300 milliseconds. How do we come up with that? Well, 3/10 of a second is going to be what? Well, 3 divided by 10 ends up being 0.3. So the 3 divided by 10, we changed to 0.3. And then that's how many seconds that we have. But if we want to change that to milliseconds, then we're going to have to do something here, because we can't keep that same unit. We've got to change it. Now the question is, what do we change it to? So what I'm going to do is I'm going to take that and I'm going to multiply it by a conversion factor. So we want to get rid of the unit here of seconds. So when we do that, what are we going to have to do? We're going to have to put 1 second on the bottom, 1 unit of whatever it is we're trying to get rid of. That way those two cancel. So since we're looking for units of milliseconds, what we're going to have to do is we're going to have to figure out how many milliseconds are in a second. So if I go here, let me stop this for just a second and come back to that. If I go here, this sticks with it. If I go here and I find out milli is 10 to the minus third. So if I have a millisecond, then I have a 10 to the minus third of a second. So if I have 10 to the minus third of a second, that means I have what? Turn on the annotation here again. I'll just put this over here in text and kind of write it over here. So if I have 1 second is going to be equal to how many milliseconds? Well, if I take 10 to the minus third of a second, that's taking 1 second and it's dividing it by 10 times 10 times 10. So that it's going to divide that second into whatever this number happens to be. Now, that's if I want 1 millisecond. Now, how many of those milliseconds are actually in a second? As it turns out, in each one of those seconds, a millisecond is going to be 1,000th of a second. I should have written that a little bit differently there before, but 1,000th of a second. If I collect 1,000 of those, I have 1 second. So 1 second is going to be equivalent to 1,000 milliseconds. So if I go here, and unfortunately, when I close that out, I'm going to have to. There we go. In order to keep this conversion factor the same. So there we go. My writing is terrible. It's milliseconds. And how do I know this? How do I know that there is 1,000 milliseconds in a second? How can I use this particular conversion factor? This is the same as multiplying by 1. If I were to take both sides here and divide it by the unit on the other side, I would get 1. So because of that, technically here, I'm only really multiplying by 1. So this And sorry, the tool here is not that great. So if I take 0.3 and multiply it by 1,000, I get 300 milliseconds. And that's where that answer comes from. So basically it's figuring out how to take the unit that we're given, which in this case is the seconds, and then converting it to the unit we need. And it's done through these conversion factors. Okay, so that looks a little messy there. Sorry about that. How fast does a 2 kilogram object have to move to have kinetic energy of 1 joule? Now let's see. I'm going to put that particular tool away. Did I start here? No, I did not. Okay. All right. So something I want to remind you of is that 1 joule is, of course, a measure of energy, but it is also equal to, I guess I'm going to have to pull that back up. 1 joule is the same as 1 meter squared per second squared. Why do I bring that up? Why is that important? Well, it's important for this reason. If we're looking to see how fast this object has to move to have a kinetic energy of 1 joule, we know that 1 joule is equal to 1 kilogram times, sorry, start off with this 1/2 times m times v squared. How do I know that? Because the energy that this thing has is kinetic energy, and I'm measuring the kinetic energy of an object that's moving through the formula 1/2 mv squared. That's how you measure kinetic energy. So in this particular case, I happen to know that we've got 1 joule is equal to 1/2 times 2 kilograms, because I know that's the mass of the object, times velocity squared. So because I know that, and I'm going to have to move this up here so I can have a little room. Because I know that, the only thing that I don't know in this particular formula is the velocity. So when I go through and I do the multiplication here, I get 1 joule is equal to, now the 1/2 multiplied by the 2, those two items end up becoming 1. I'm still left with the kilograms over here, times v squared. If I divide both sides by the kilogram that's there, the 1 kilogram, then the kilograms disappear on both sides, but I'll go ahead and show that. So on this side, if I take 1 joule, which we've already know is kilogram times meters squared over second squared. So we know that. And we're going to divide that by a kilogram. We know this is equal to the velocity squared. What that tells us is that the kilograms cancel. And so over here, I've got 1 meter squared divided by second squared is equal to v squared. So how do I get the velocity squared by itself? How do I undo a squared operation there? What undoes a square operation is taking the square root. So when I take the square root of both sides, which I'm going to label with this, that means 1 meter per second equal to the velocity. Or in this case, the speed, since we simply don't have any idea as to what the direction of the motion is. So, okay. Things are getting a little messy here, so I'm going to kind of clear things out so it's a little easier to see. But you have the answers there. You can go back and look at that. Say a substance has a density of 4 kilogram, let's try that again, 4 grams per cubic centimeters. Express this density in terms of kilogram per meters cubed. So again, how do we go about changing that? Well, a couple of factors here that we're going to have to use. Let's see, I'm going to go ahead and put them over here on this side of the screen, make it a little easier to use. 1 kilogram is going to be equal to 1,000 grams. The other unit that we're going to need is we've got to figure out exactly how many centimeters there are in 1 meter. We're not going to factor in the fact that it's cubed just yet. We're just going to look at centimeters to meters. If you need to go back to the chart, we can go back here, and I tell you what, this is going to force me to do this. Okay, let's just kind of pull you over here, stop that, and then go here. If you need to refer back, you can go back here. So centi means you've got 1/100th, because this is the same as 1 over 10 squared, which is 1 over 100. So it's basically 1/100th. So if you take a meter and you divide it by 100, how many centimeters would you end up with? Well, you would end up with 100 centimeters equal to 1 meter. Now, is that where it ends for this particular problem? Well, not quite. What we're going to do is we're needing cubic units. Right now, the units that we have are just to the first power. They're just linear. We need to change that into a cubic unit. Here's how you do that. Basically, we're going to take 100 centimeters is equal to 1 meter. And we're going to raise that to the third power. Now, when we do that, we end up with 100 raised to the third power of centimeters cubed is equal to 1 cubed meters cubed. Now, 100 cubed is going to be, let's see, how many zeros? You should end up with 2, 4, you should end up with 6. Because 100 times 100, let's say it's 1,000, 10,000. So if you do it again, should end up with 6 zeros. There we go. Another way to write this is that if you multiply 10 by itself 6 times, then you should end up, and let's say 10 times 10 is 100. If you do it again, that's 1,000. So that's 3 tens multiplied together. So if you take 1,000 multiplied by 10, that is 10,000. That's 4 tens together. Multiplied again, it's 100,000. And you multiply it again, it's 1,000,000. So that's 1 meter cubed. Why is that important? why is any of this important? Okay, so over here we've got 4.0 grams per cubic centimeter, but we're wanting to change that. So how is it we're wanting to change that? We're wanting to change that into kilograms per meters cubed. So what are the conversion factors? Well, we know we've got grams, so we need that to cancel out. So we need kilograms on top. So that should cancel that out. The other thing that we're going to need is we're going to need to change that cubic centimeter there to cubic meters. So to do that, we're going to need to have sorry for all the extensions and whatnot. It's pain, I know. That's 1 meter cube. So we end up with units canceling. So the gram here cancels with that gram here, and we're left with kilograms. The cubic centimeters here, which is technically in a denominator, and since we've got this in the numerator, and that is technically raised to the third power, those two cancel, and we're left with the meters cubed in the bottom. So we have 1 kilogram because that's what we ended up with out of that part. But we also have 10 to the 6th here in the top. And we also have 1,000 there in the bottom because those numbers don't disappear. They come along here. Well, the grams do cancel. The value there, that 1,000 still hangs around. It's just the units that cancel. And the units of the meters cubed still comes along because that's in the denominator. We haven't canceled that out yet. So technically, we end up with 4.0 kilograms times 10 to the 6th divided by 1,000. So I've got 6 tens in the top. And if you look at it closely, I'll have 3 tens in the bottom. So 3 of those 10s cancel out with 3 in the top. Leaving us with this. So that's the same as 4.0 times 10 raised to the third kilogram meters cubed. That is a long expression or a long process there, but that's where it comes from. So you can play that recording back as much as you'd like in order to be able to go through and read that. Okay, what about number 5? Number 5, we want to change 0.05 milliamps to, I believe that is microamps. And let's see if I am correct. Yeah, mu. Mu and this Greek symbol, those are the same things. So basically, we're going from a milli, 10 to the minus 3, and we're cutting it to micro, which means we're making it even more fine. So what is the difference between milli and micro? If I have this amount of something, and if I cut it into pieces, if I cut it into 1,000 pieces, then basically I will end up, if I can type this correctly, times, let's see, 1,000 times 10 to the third micro something. So what we're going to end up with, and I should put there, didn't do that before. So in other words, we're going to have 1,000 more of something if we go to those units that are basically 1/1000th of whatever it was we were looking at before. So in a case where we are, get this out of the way, in a case where we are trying to take a unit that is measured in milli and convert it to micro, we take the milli, and we're going to end up multiplying it by 1,000. And that means we end up there. And that should not be 50. Sorry, that should be 0.05. So if you take 0.05 and you multiply it by 1,000, that means the decimal point moves 3 spots over to the right. And that's where the 50 comes from. Okay. Now, as we move along here, we're going to go into more and more of a use of physics in this. So far we've been doing a lot of conversion factors, but now we're actually going to be moving into physics a little bit. All right, so an alpha particle of mass 6.64 times 10 to the minus 27 kilograms is accelerated from rest through a potential difference of 20,000 volts. Now you may go back and you may look through some of the physics material there to figure out that you can accelerate particles through a potential difference. And when you do that, whatever the charge is multiplied by the voltage will end up giving you a measurement here in electron volts. And that's what this sheet is supposed to help clarify. So let's calculate the final kinetic energy in electron volts and then the final speed of the particle. So you can see the answers here. All right. Since we're talking about an alpha particle is going to have a charge that is it's basically 2 protons and 2 neutrons. That's an alpha particle. So what's the charge on that? Well, the charge on that is basically going to be 1.6 times 10 to the minus 19th coulombs. Since we got 2 of them, I multiply it by 2. The voltage in this particular case is 20,000 volts. So because it's 20,000 volts, I just type that in there. So I've got those 2 together. When I multiply those 2 together, a coulomb multiplied by a volt is going to end up being a joule. Now, the problem is that the problem is actually asking for 40,000 of the answer in keV. So because of that, I need to figure out how in the world I change the number of joules that I have here into electron volts. So the way I do that is I take the number of joules and then divide that by the number of joules that it takes to produce an electron volt. So in other words, I have this number of joules. I'm basically saying, okay, 1 electron volt divided by this is going to be equal to 1. So I'm going to multiply it by that. So if I take this and divide it by that, I come up with the electron volts. And since it comes up with 39,945, that is something that's very, very close to the 40 keV. Now, what's going to be the speed? The speed in this particular case is going to be energy is 1/2 mv squared. This is going to be the kinetic energy, and I should go ahead and write it as such. So this is the kinetic energy, and we're not looking at the rest mass or anything of that sort. We're just looking at the kinetic energy, and that's what this is going to be related to. So I know that the kinetic energy is going to be equal to 1/2 mv squared. I know that this is the energy that we've got right here. If I take this particular formula and solve it for V, this is what I come up with. Basically, I take this, multiply both sides of this equation, which I should go ahead and just put in the equation right there. And if you're in Excel and you don't want it to do silly things like that, you put a single quotation mark and it just keeps the text. So if I multiply both sides here by 2, divide by m, that gives me v squared is equal to the mess on the other side. In order to just have v squared left, I take the square root of both sides. When I do that, basically I take this value, multiply it by 2, divide it by G5, which is this, because that is the mass of the alpha particle. And I come up with this value, 1,388,420 meters per second. So I just rounded it to this. Now, I go through those same calculations here. And rather than use an alpha particle, I'm going to use an electron. Here's the mass. And basically, this is the same type setup here. I'm going to use the mass of the electron. This is the charge on the electron. Now, remember, when I had up here, when I was dealing with the alpha particle, I had 2. Here, I've just got 1. So just keep it at 1. Got the same voltage, produce the same energy, go through that same conversion process here in order to be able to produce this in EV. What I'm going to do here, just to kind of just copy and then paste. Okay. All right. Same formula. It works out the same way. I'm just dealing with a different particle. And this is what I come up with. It's 83,816,746. So that's where that number comes from. And this obviously comes from the computation above. Now, is the neglect of special relativity justifiable in part A? Is it in part B? And then why? This comes down to basically, do we need to factor in special relativity, and how do we judge that? We judge that anything that starts to move close to the speed of light, and by close I mean if anything can get within 10% or more of the speed of light, then relativistic calculations need to be factored in. Now, I'm not going to ask you to do that kind of thing. What I am going to ask you to do is to see roughly how this relates to this. This is the speed of light. This value here in reference to the speed of light is only about 0.46%, nowhere near 10%. So in that particular case, no, we don't have to worry about putting it in here. Here, on the other hand, we're looking at something that's getting close to 28% of the speed of light. Yeah, relativistic effects do need to be taken into consideration here. So for part C, calculate the rest mass energy of 2 protons and what is the ratio of the mass of a proton to that of an electron. So for part C here, how do we calculate that? What is it we're asked to do again? Calculate the rest mass energy, and we're given the mass of a proton here. So what is the rest mass? Well, here we've got 1.67 times 10 to the minus 27. That's what we had here. So the mass of 2 protons is going to be basically the mass of a proton times 2. So that's going to be m. We know what the speed of light is. Again, that's listed over here. So what's the energy? Well, the energy is going to be this times that squared. Multiply the two together. These are the units that come out of that. And as it turns out, the energy here should end up being in joules. If we convert that to EV, then we have a whole bunch of EV here. If we want to convert that into something that's a little bit more usable, like mega electron volts, we take it and we divide it by 1,000,000. And that's where that number comes from. I'm going to leave it to you to go through and to figure out what the mass of a proton is, what the mass of an electron is, and then you take that value and divide it by this one. It's really not that hard. All right, problem 7. All right, problem number 7. A charge of 20 nanocoulombs is collected from an ion chamber that is irradiated in a linear accelerator beam. To how many electrons does this charge correspond? Well, it collected, let's see, how much you know? 20 nanocoulombs. Okay. Each electron has 1.60218 times 10 to the minus 19th coulombs. If this is the amount of charge that was collected, then I have this number of nanocoulombs for every electron that's collected. This is how much charge that is measured. So if I take this and change it to coulombs, remember, I've got to do that unit conversion first. If I try dividing this by that immediately, I'm going to end up with the wrong answer. But if I change this to coulombs, which is what that is doing, basically multiplying it by 10 to the minus 9th, and then divide by this, that gives me the number of electrons, or 1.25 times 10 to the 11th. Which is, since I changed the number here, that I didn't bother to go through and change the value here. So mea culpa on that. There we go. All right. If that is collected over half a minute, what is the current in units of nanoamps? Not used to saying that word. Pardon me. So we have the amount of time that it takes. So if I take this amount of charge and I want to figure out how many nanoamps that's going to be, I need to take the amount of charge that I see here and divide it basically by however many seconds I have. If you'll remember back, and you may or may not, but if you'll remember back, the current is going to be defined as how much charge moves by a specific point in a second. So if I take the amount of charge that I have here, and that's in a current, and it moves by that particular point in 30 seconds, then the current would actually be that charge divided by the number of seconds, and it turns out to be that. So it should end up being 0.67, I believe. All right, part 8. Derive the formula lambda is equal to h, that's a constant, times c divided by E for the wavelength associated with a photon of energy E. So here's a hint. Speed of light is equal to the frequency times the wavelength. So there's another formula here that you're going to need in order to be able to derive this particular formula. I will go ahead and give that to you now. Is equal to, and let's see if I can insert the symbol here. So I will see if you can make the substitutions of the variables in here to solve for this. I think you can do it. If you can't, just give me a shout or talk to one of your classmates. That'll work too. All right. So from this, derive this particular equation. So if you know what the velocity is, and you can divide that by time, then you come up with basically the difference in the velocities divided by the difference in the times. That's going to end up giving you the acceleration. Actually, you know what? For this particular part, just take that out. I don't think that's necessary for you guys. So don't worry about that. Don't worry about 8b. So skip. All right. So what wavelength is going to be associated with a 20 keV proton? All right. So what wavelength? All right. We have 20 keV. If you convert keV to joules, or the other units here that go along with it, and let's see, we're wondering what the wavelength is. We know what Planck's constant is here. We know what the speed of light is because we can look both of those up. You can use Google or what have you. If we use that same formula that we had before, plug everything in, this is what we come up with. In other words, B3 times B4 divided by B2. And this is what we come up with. And I really should replace that with 0.620. And I didn't do it. Yeah, wait, did I have that right? Oh, 0.062, sorry. Silly goose. All right. There we go. How does the wavelength compare to the size of an atom? You can look that information up and you can see how roughly they compare. I will leave it to you to go through and define the SI units for all of those. This is also readily findable information. As a matter of fact, I've got a presentation or two that has a lot of that information in there, so I'm going to leave that to you. You can describe briefly the nature of electromagnetic waves, compute the frequency and wavelength of a 200 keV photon. I'll give you a little help with that. We know what the energy is of the photon. We know what this particular formula is. It links Planck's constant with the frequency. Since we have the energy, we can turn around and we can solve. So if we take the energy and we divide it by Planck's constant, we end up with this. If this is going to end up being cycles per second, And so we can change that to hertz. That's where that comes from. The wavelength here, we know how the wavelength and the velocity, if we multiply that together, we get the speed of light. So that's where this computation comes from. I don't know if I made I don't think those values are accurate. So we'll just get rid of those. Okay. What is the frequency of an electromagnetic wave of 6 cm? Let's see, did I work this out? I guess I didn't work this out. Okay. There we go. Basically, what you are doing here is if you know what the wavelength is, you know what the speed of light is, you can go through and you can compute the frequency. And then you can determine, what part of the spectrum that might be in. This is a little different. I had to go out and I had to find a source that had this information in it. Basically, if you do a search for finding tungsten and KeV, let's see, orbitals. See if we can find. Thought I had. See if we got them in images. Approximate binding energy. I think there may actually be something in the textbook along this line. This is for tungsten. So you can see the approximate binding energy here as you go from the K to the L shell. This is saying roughly 59. It pretty much depends on how accurate your measurements are. I think this one's pretty well rounded off. This would be closer to 57 according to that document. If you know what the energy is of the emitted photon, again, you can use the processes that I've outlined to find the wavelength. So anyway, that's this particular exercise. I wanted to go over a lot of that with you so that you had some method, some grasp as to how to do that. And I hope this helped.